Hello, good morning. So this video actually is going to go through a whole bunch of different standards. So just make sure that you are watching the C-Pulse video for these standards. So for this one, it's going to have I believe 3 to 4. So for this particular standard, investigating and describing the transformation of energy from one form to the other. You're going to also be citing evidence to explain that energy cannot be created nor destroyed, only changed from one form to another. So it's very similar to the one we just saw. And then we're also going to observe and describe that heat flows in predictable ways, moving from warmer objects to cooler ones until they reach the same temperature. So very similar process. So if you do have your textbook, this is the page we are on from 14 to 20. All right, so heat is transferred around us all the time. If they weren't, nothing would ever change temperature. Heat doesn't transfer in random directions, though. Heat is transferred from warmer areas to cooler areas by conduction, convection, and radiation. Conduction is a transfer of heat from one particle of matter to another, within an object or between two objects that are in the direct contact. Conduction occurs when you place your head on a cool pillow. The fast-moving particles of your skin collide with the slow-moving particles of the pillow. This causes the particles in the pillow to move faster, and the pillow becomes warmer when your skin becomes cooler. So just remember, conduction is always, well, actually just heat transfer in general. It's going to be from hot to cold. Most people believe that when you put something in the freezer or when you put something in a cold room, we are getting cold because the cold air is making us cold, but it's actually the complete opposite. Our warm body or the warm object that you put in the freezer is going to be letting off that heat and is going to be transferring that heat onto the cold area, and that's why it's going to get cooler, because it's coming from this hot to cold. Now, convection, on the other hand, is a type of heat transfer that occurs through the movement of fluids, which can be a solid, liquid, or gas. Fluids are materials that flow. When air is heated, a particle speeds up and moves further apart. This makes the heated air less dense. The heated air rises to float on top of the denser, cooler air. Cooler air flows in its place, heats up, and rises. Previously heated air sinks, and the cycle repeats. This flow creates a circular motion known as a convection current. Convection currents in the air cause wind and changes in weather. So remember, we've talked about convection currents before, not necessarily in water or anything like that, but we have talked about an Earth's crust and the sun's surface, which you will learn in 8th grade. But in the Earth's crust, right, we talked about convection currents a lot. Remember about density. So the bottom part is obviously going to get hotter faster because it's right on top of the stove. So that's hot material is going to be going up because it is less dense. Then it's going to cool down right on the top, and it's going to become more dense and flow down. So this is going to create the circular path coming from that bottom up, and then that up to go to the bottom. So this convection also occurs in boiling water. So if you're boiling soup, anything like that, that's going to have a liquid or a gas. Like I just said, it does happen in our weather. So that's why we have our weather patterns like cold fronts, warm fronts, things like that, because of these convection currents that are going to be occurring depending on density. So convection is all about density and liquids and gases. Sometimes solid, just like in Earth's crust. Radiation, on the other hand, we should be very familiar with it. We live in Florida. So radiation is just the transfer of energy by electromagnetic waves. Radiation is the only form of heat transfer that does not require matter. You can feel the radiation from a fire without touching the flames. The sun's transfer of energy to Earth is another example of radiation. Sunlight travels 150 million kilometers through empty space before it warms up Earth. So think about it like this. Remember, radiation is coming from the sun, okay? Or we can say UV rays. Ultraviolet rays are coming from the sun. Remember, they do not need a medium. We did talk about that. Not all electromagnetic waves are going to need something to travel through. And in particular, UV rays, right? We have the sun that's many, many millions of miles away. But indeed, when we go outside, we can still feel its warmth, like if it was very close to us, but it's really not. So that would be a good example of heat transfer using radiation. Also, you can think of going to the beach, right? So we have these convection currents. When parts of fluid is heated, rise and is replaced with cooler fluid. So as fluid rises, fluid above it cools, it sinks, and the process repeats. So if you're in, or for example, if you're in the ocean, you're gonna have that top portion of the water be a little bit warmer than that bottom portion. It's going to get cooler, right? Because it doesn't have that source of heat. Now we can think of going to the beach also by conduction, that is going to be touching your feet with the sand. So conduction is going to be occurring when heat transfers between particles of an object or between particles of two different objects in direct contact. So as we walk on the beach, the sand is going to be very, very hot, right? So it's going to be conduction because it's directly touching. And now we have radiation, where radiation occurs when heat is transferred by these electromagnetic waves, like we just said. And this type of transfer does not require matter. So those would be our three types of heat flows that occur, let's say, when we go and to the beach or things like that. Now, also, we do need to think of energy transformations as something that can be transformed to one thing to the other without losing this energy. So in conduction, convection, and radiation, energy is transferred from one place to another. Even though the energy moves, it is always conserved within a system. For instance, in the pizza, or when we go to like a restaurant, we have like this pizza oven. The oven is going to lose energy, but the pizza is going to gain that energy. So total energy of the oven pizza system is conserved by the law of conservation of energy. Energy cannot be created or destroyed. So anytime you lose energy in one way, something else must be gaining it. So for example, if I am baking bread, for example, the oven itself is going to be emitting this energy source, right? And then it's going to be losing this energy source to the bread because that's what I'm baking. So the bread is going to start rising. They're going to start gaining all this energy. And that's going to be given off by the oven. But in itself, when you take into account the oven and the bread, when you combine those, you have this overall conservation of energy that is very important to understand. Also, all physical processes involve energy. So the law of conservation of energy applies to everything, even when energy changes forms. So some forms of energy related to particles include nuclear energy, thermal energy, electrical energy, electromagnetic radiation, and chemical energy. These different forms of energy transfers to and from one another all the time in our daily lives. For example, electrical energy used in homes and businesses is often generated in power plants by burning fossil fuels, such as coal, oil, and natural gas. The chemical energy stored in fossil fuels is released when it is burned. The power plant transforms this energy into electrical energy. A lamp uses this energy to light up a bulb that emits electromagnetic radiation. Remember, a light bulb is going to emit this electromagnetic radiation as visible light. We can also say heat is going to emit heat also. So just make sure that you know that these transformations happen every single day. For example, when we put ice in our water, when we put ice in our juice, same process. That warmed up drink or anything that you want to cool down is going to emitting this heat off to the ice. The ice is going to start to melt, not the other way around. Most of us, yes, ice does cool it down, but technically the warm drink is is warming up our ice cube. Many energy transformations involve thermal energy. So for example, an electric stove is going to be able to transform electrical energy into thermal energy. Another kind of stove is a gas stove, which converts the chemical energy from natural gas into thermal energy. Thermal energy can be transformed to do work. For example, some types of train engines heat water to create steam. This causes pistons in the engine to move. The thermal energy of the water is transformed into the mechanical energy of the train. So that's why it's very important. Same thing to understand the difference between thermal energy and heat. So if you want to think about it, right, we should definitely know our definitions. So thermal energy, remember what we talked about before, is going to be the total energy that is inside an object. So they do not necessarily have to feel hot, for example, because it's also the total amount of kinetic and potential energy in an object. Now, heat, on the other hand, is just the transfer from a warm to cool object. That's all that heat is. So heat does not necessarily, well, heat is going to be measuring this hot or cold object because we're transferring this hot to cold, but then thermal energy is just going to be the total energy within a system, whether it's kinetic or potential. So usually though, if something's very, very hot, then our thermal energy is going to be very high because it's going to be measuring that kinetic energy and potential energy that is together, right? So something's going to be hotter. But if you have, let's say, 2 ice cubes, right? 2 ice cubes, same temperature, same everything. But let's say one ice cube is down on the floor and one ice cube is on the cabinet. Theoretically, the one that is on that cabinet is going to have a higher thermal energy because your thermal energy is the amount of kinetic and potential energy. And potential energy is determined by height and molecule move and its position, right? So since the ice cube is at a higher point than the floor, then it's going to have a higher thermal energy. So make sure you know those two distinctions that are very important. So I'm actually going to pause here. Make sure you're taking very, very good notes because we will be having some sort of a test coming up very soon. Thank you.